questions before we get started? No? So again, I'm holding office hours since yesterday was a holiday and I didn't have office hours. Wednesday, I was out of town. I'll be holding office hours today, right after class, right here, for any questions you might have, either about the homework or about your projects. All right, so let's get started then. So we're going to continue with the topic of correlation and fitting lines to data and learning more about the regression line. I'm going to go back to the example that you saw on Wednesday, which was the pre-molt and post-molt size of the Dungeness crab. And we'll start there, and then we'll go on to another example. So first, let's just take a look at the size of the crab before it molts. It's pre-molt size. And again, that's the width of the shell, the main portion of the shell at its widest point, measured in millimeters. And I have a question for you, is what's the center of this distribution? So roughly, if you needed to come up with an estimate for the center of the distribution, that's the balance point of the histogram. It's the average of all the values of carapace width that were measured on these crabs. What would you choose? Yeah? 130, 135? So why did you pick 135? Of the mode. The mode looks to be roughly at 140, but it has a bit of a long, well, it's asymmetric, and it looks like there's more mass to the left of the mode. So you're bringing it down to 135. Anybody else? That's a pretty good guess. Here's some more information. I added a rug to the density plot. And now you can see all the, well, kind of, you can see all the individual measurements, although there's some overplotting. And what do you think the spread is for this distribution? Now remember, what the spread says is, what's the average deviation from the center? So if we took the center to be about 135, and we're looking at how individual crabs deviate from that center, what would you, 10? Who said 10? That's a good, yes. 10? And what reasoning did you give? It's a good number. So you said, well, if I went out to get most of the data, that would be roughly 2 SDs, even though this isn't exactly normal, right? And so that you're thinking 155 to 115, and so maybe it's about 10. That's good. You know, having this sort of slightly asymmetric distribution makes it a little hard for you to just simply eyeball it. But you both did a good job. The actual center is 132, and the spread is 10.5. So if you knew nothing about a crab's post-molt size and just had to say, on average, the pre-molt size is about 132 millimeters, and I would expect deviations as big as 10.5 or even 20 millimeters from this center of 132. Now, something changes when we can see pairs of measurements where we have post-molt size and pre-molt size, and you can see that they're highly correlated. That these, this is just a sample of 100, and I chose that because when I plotted everything, it was really hard to see individual crabs. So I took a random sample of 100 of the crabs that we have and have plotted this. plotted their pairs of post-molt and pre-molt. So on every crab, we have two measurements, pre-molt and post-molt. That gives us our scatter plot. And if I have knowledge, for example, if I have knowledge that a crab is, let me see if I've got this. Here we go. Sorry about that. If I have knowledge that a crab is about 135 millimeters across in its post-molt size, then what would you estimate for the center and spread of their pre-molt size? So what I've done is I've added little gray dotted lines dividing up the post-molt size into 5 millimeter increments. And so right here we can look at 135, and then we can see the post-molt, we start at 135 as a post-molt size, and we can go up and see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9 crabs that fall into that little interval. So those 9 crabs are roughly all the same size in terms of their post-molt size. And I want to say, okay, well, on average, what's their pre-molt size? And what's the spread about that average? So now I'm looking at a much smaller, more homogeneous population, subpopulation. On the other hand, I could come up here to 160. That's looking at the post-molt size of 160. And I go up. I chose these two on purpose because they don't have a lot of dots in them, and you can sort of see, you can actually see the individual measurements. So I look up, and I see that there are also about 9 crabs that fall into that little interval. So there are roughly 9 crabs here that have a post-molt size of about 160 millimeters. And if you knew that about the crab, what's your best estimate for their pre-molt size, and what's the spread? So to give you a little more information, what I did is I made rugs for these. But it's the rug of the pre-molt size. So for each, you'll see that there are 9 little threads on the lower rug. 2 of them are actually very close to each other. That's why it's a very thick red dot. Those are the measurements of pre-molt for the 9 crabs that are in this 135 interval. And then for the crabs in the 160, you look across, there's a rug up high, and those are the 9 values of the pre-molt size for those crabs. Yes?
I was just wondering, is there a reason why you chose like 5 on either side of 135?
It's 2.5 on either side. Just, yeah, so what you mean, why did I pick an interval of this size? Well, basically, I wanted 2 reasons. One is convenience. 5 is a nice number. And the other is that I wanted to have the interval small enough so that I can consider the crabs nearly all the same size. So, but not so small that I wind up without any data or one point in the interval. So who wants to venture a estimate of the center of the pre-molt size for crabs who are 135 millimeters in their post-molt size? And attach a spread to it. So roughly, what's the average of the pre-molt size for the crabs that fall into this interval, centered at 135? Yeah? 120? That sounds like a good estimate. And what about spread? Can you give me a sense of spread? Well, is it 10 like it was before? No, definitely not. There's yeah? About 7.5. That's the, so not the range. I'm asking for the spread. So there's been some confusion in the past about range and spread. Range is minimum to maximum. Spread, I'm talking about the SD. So the typical deviation, which is from the center in one direction or in the other direction from that center. So it's going to be less than that, right? About 3? Anybody, any other guesses? 3 just about encompasses everything. So it's probably smaller than 3, right? Yes? Spread of 2? Did you do some calculations? No. 119 with a spread of 2. All right, so 119, 120, and a spread of about 2. 2 seems about right because, yeah, if we look at 120 or 119, it's not really symmetric, but it does look like if we went up to 121 or 122 and down to 116 or 117, that we would get a good proportion, but not all of the crabs. How about the other one, the 160 millimeters? What's your estimate of the pre-molt size, the average pre-molt size for those crabs? Yeah? 145? That looks good. These look slightly more clustered and symmetric, about 145. And spread? Do you think it should be smaller than the other one, right? Maybe 1.5 or so? So the distribution of the pre-molt size, which we started with, has its particular center, which was 132, and a spread, which is its SD, which was about 10.5. Now, when we can focus in on a particular subset of crabs that have all the same post-molt size, those crabs are more similar to each other, and knowledge of the fact that it's 135 versus 160 says that we can have a much more narrow range of pre-molt size, and the actual center is 119, and the spread was 2.2. For the crabs that were 160, the center was 145, and the spread was 1.4. So when there's pairs of information, such as post-molt and pre-molt, and they are highly correlated and that says that there's a strong linear association, then knowledge of post-molt size is looking at a very small subset of the larger set of values, and we can come up with more the center and spread of that subset for the other variable, the pre-molt size, will be different than for the overall. And we can actually come up with good estimates of them knowing the post-molt size. So you saw this picture on Wednesday. This is a picture where for every 5 millimeter increment, I took the average pre-molt size. And those are those red squares. Then they were connected the dots to see that they almost fall on a line. And Mike went over with you about how to fit a line to all of the data and see that that line tends to go through these graph of averages when you've got this linear association. And that's the blue line. It's the regression line. You can think of it as a smooth version of the point of averages. So what are the errors like with that when we use that line, if I back up? So the beauty of this regression line is that now when I want to make a statement about the pre-molt size for crabs who have a post-molt size of about 135, I can plug 135 into my regression line and read off the pre-molt size. And if I have a crab that's 160 millimeters wide in its post-molt size, and I want to make a statement about its pre-molt size, I can read off the graph of, read off the regression line of my estimate for the average pre-molt size. But of course, not all the points are falling on that line. So these little blue line segments are looking at the errors that I incur when I would use the line and compared to the point on the line compared to the actual point. Those are called residuals. These are the deviations from the actual observed value to the estimated value based on the regression line. So if a point falls below the line, then that deviation is negative. We take the value of the actual observed value and we subtract off the estimated value based on the regression line. And so these are deviations only in the vertical distance because we're looking at the error in our prediction for pre-molt size. And the line that was fitted, this regression line, minimizes those deviations squared, the root mean square of those deviations. These are the deviations in the y direction in pre-molt size. So we can think of the regression line to a scatter plot is like averages to a rug plot. So if we back up and see, here's our rug plot, and the average of all of those values was 132. So that's a sort of a point in the middle of the rug, in the center of the rug. Now, when we've got a scatter plot of many points, we can think of that regression line as is to the scatter plot what the average is to a list or what the average is to the rug in our rug plot. Likewise, we can think of the spread about an average is to a list as the root mean squared deviations from the line is. So if we look at the actual formula, we've got these values of these pairs. That's really important to think about is when we make scatter plots, it means we've got pairs of values. Some of you on your projects have data, you've got many, many possible pairs. Those of you who are working with the spam data, you've got 30 different variables. You've got lots of data, lots of many measurements on a single email. Whether or not it's spam, the number of capital letters in the subject line, the number of exclamation or punctuation marks in the subject line, those are all variables that are being measured on the same email. So you've got lots of pairs or triples or quadruples or 30 tuples of information about any single email. So here we have our observed value where what's xi in the problem that we're looking at? What's xi? In words, what's non-notation? What does xi stand for? From a previous plot. I'm referring to xi here. There's some xi here on this plot. What is xi? Post-molt size for a specific crab, right? For the ice crab in my list of crabs. And yi is the pre-molt size for that same crab. Mike derived for you the regression line last Wednesday. And that is, and if we take the post-molt size and we plug in, or we look at what value is on the regression line for the pre-molt size, that's called yi hat. That's maybe your predicted value for pre-molt size based on the regression line. Then the deviation are the errors, the residuals, like how far away is the actual value for the crab. Oops, there should be a sub I on the y hat. yi minus y hat I. What are those deviations? Those are the residuals. So then I can look at the root mean square error. Remember the SD of a list we defined as a root mean square error where the error is about the mean? Now I'm looking at the root mean square error, and the error now is the error in the residuals. The deviation of the actual y value from the point on the line, the y value on the line. So that's the yi, the crab's actual pre-molt size, minus yi hat, which is the point on the line. That's the xi, yi hat point on the line. So just like the SD was the root mean square error of the, each of the values on the list about its mean, this root mean square error is about the y values about their predictions. Again, there's an I missing from my subscript. It should be y hat sub I. And if you do the calculations, you can see that that is, in fact, the square root of 1 minus r squared times the SD of y. So that's saying that the errors associated with using the line, the deviations from using the line, are much smaller than the actual deviations in pre-molt size, because our correlation was really high from, let me just stop there. Our correlation is really high between pre-molt and post-molt size. If we take 1 minus r squared, we get about 0.4 square root of 1 minus r squared. And so the standard deviation, the spread now about the line, is about 0.4 of the actual spread in the pre-molt size. And that's because this is associated with those pictures here where it says, if you know something about the crab's post-molt size, that narrows down the pre-molt size. And those are the deviations that we see here are all really small about the line in comparison to the overall deviations about the mean of y. Okay, so this is a plot of the residuals. So I'm now plotting the post-molt size, a new pair, post-molt size and the residual for every single point. And you can see that basically this is what you want to see, which is no patterns whatsoever, just a blur of points going across post-molt size. That indicates that the fitting a line to this data, or that there's a very good linear association between post-molt and pre-molt. We look at these are called residual plots. We look at these residual plots to help us determine whether or not it's appropriate to be fitting a line to the data, whether or not a linear association is appropriate. We'd like to see, I've put a horizontal line at 0, and I'd like to see scatter that's sort of uniform in either direction, and just like this one.
Wait, so those are standardized residuals?
Oh, they're not.
Oh, they're not.
They're not.
Oh, they're millimeters.
Yeah, they're still in millimeters.
Okay,
Yeah,
because otherwise I was kind of wondering how we would get a 4, but okay.
that's why.
All right, good. Thank you.
So in general, there are many kinds of residual plots you can look at. The two that most commonly used are plotting the residual and actually this should be flipped around, should be x in the residual or y hat in the residual. And we look for patterns. And we really like to see no patterns, which is what this is, no pattern. And that tells us that the relationship is well represented by a line. The relationship between x and y is well represented by a line. If there's some sort of curve in the residual plot, that's saying that it's not well represented by a line, and that you might want to do a transformation or even to add additional variables. If there's funneling, which means if the spread gets larger as you move across the page, that says that the size of the error varies with the size of x. So your estimates are still okay, but the notion of using the spread as a good estimate of the accuracy of your regression line is changing with x. All right, new example. What do you think of this? This is going back to our infant data in the Kaiser. We're looking at the moms now, just the moms. We're looking at their height measured in inches and their weight measured in pounds. Do you see a linear association there? there. It's just nowhere near as strong. Well, there are some other issues going on with this plot, right? What do you see? What sort of strange, what's a little bit unnerving maybe when you look at this plot and you're thinking, is there a linear association here? Yeah?
It seems like people are more vertically constrained than they are horizontally.
Good point. People are more vertically constrained than they are horizontally, okay? Meaning you can't do nature. It's hard to adjust your height. Nature kind of gives it to you. But weight has more than nature. It also has nurture or nutrition involved. And so where do you see that? How does that come out in this plot?
There's lots of points that are high up.
So there's a lot of scatter going up across the whole range of heights, that there's the points kind of are fading up really high, if that's one way of describing it. But you can still see a general, can you see a general elliptical shape in there? But we've got this other problem of basically nature and nurture involved. So what I'd like to do is take this. You see there is a correlation of 0.43, but that's still, you can always compute a correlation. That doesn't necessarily mean that there's a linear association just because there's a correlation. The correlation is just a computation. Right? So what I'd like to do first is show you what observation you were making, is take a look at a slice of the women. So here's a slice of the women that are 61 inches tall to the nearest inch. So that's taking a slice right about here and looking at the distribution of their weights. And you see that, that there's a bit of a long right tail here. We can do the same thing for women who are 66 inches tall. There's a bit of a long right tail, and that you see everywhere throughout these data. So if we go back here and look at this scatter plot, and you think about taking slices and looking at the distribution of weight for women that are all the same height, that sort of scatter up high is telling us that there's a long right tail for all these different values of height. Okay? But we can still try to take that that histogram, or excuse me, that scatter plot, and draw a sort of elliptical shape around the bulk of the data. So that's what I'd like you to do, is think about drawing an ellipse that encompasses, about 90% of the data or so, or 95% of the data. And so I have created that for you. Thanks. And we're going to do some work with this particular ellipse. So I'm handing out copies of the ellipse. So this is kind of an idealized picture. You know what? I need one. So, Mike, if you have extras, we need one more. Oh, okay. There you go. So the first thing I want you to do is draw a line. So, well, back up for a second. What this is kind of an idealized picture of where the ellipse is capturing most of the data points. I've taken off all of the scales on the x and the y axes, and I've just left the labels to say, okay, we've got height and we have weight. Does anybody have a guess as to what this black square is right smack here in the middle? Pierce? The average of both, right, so it's located at the average value for height and the average value for weight. And so what I'd like you to do is draw a line that goes, sort of cuts the ellipse in half. Oops, I didn't do a very good job of that. Just make my point bigger. This line is the SD line. And its slope, it's called the SD line because its slope is the SD of weight over the SD of height. And it goes through the point of averages. Now, I'd like you to take a little strip. Look at a little strip of this ellipse where if we fix the height for a certain, for one of the or for a group of mothers, like there. And you think about that little strip is filled with roughly evenly distributed points of the women who have the same height, and these are all their weights. Find the center of that strip. So is the center up here? The center's probably right about here. You can mark that. Now let's look at women that are roughly the same height, but they're smaller than average. So take another strip, vertical strip. So these are all women that are roughly the same height, and we're looking at the distribution of their weights. And find the center of that. So what's the center of that weight distribution? That should be roughly, looks like roughly about here. Now we could continue to do this for other strips as well. Let's just do one more. What about the women who are roughly, who are average height? What's the center there? That looks like it should be right on the line, that SD line. And you can imagine continuing to do this, and that's where the graph of averages comes up that we did with the crabs. So we could continue to slice this ellipse up into little subgroups of women that all have the same height to the nearest inch. And these are going to roughly fall in a line. So now that we have 3 points, we ought to be able to sketch that line. So why don't you do that? Sketch the line. So that's the line I get. So a couple questions or comments about this line. Can some people make some statements about the line? Points it passes through, slope. Jeff? Well, that's actually not quite the case, right? We actually took the center of each of those strips. Right? So the residuals should be quite balanced. So the question is, you're looking at the error about that line, right? So which line are you referring to? The new one that I just drew? Okay, if I look at this and I look in any one strip, I pick the center. So the errors involved should be balanced. And the same here. And the same here. So the error, remember now, isn't just in the y direction. So the error is in how far away is a person's weight from the average for that group? And that's should be roughly the same in either direction. Jennifer? Right, so this one's less steep. And in fact, it's this line's slope is R times the SD of weight over the SD of height. So it's less steep by the correlation. And so in this case, its correlation's 0.4, so it's a lot less steep. Any other observations? Is there one point that you know it goes through, even though this is an idealized plot? The middle one, which is what? That's right. What's that point? It's called the point of averages. It goes through the average height and average weight. So does anybody now know what the name of this line is? Exactly. This is the regression line. So where does the name regression come from? It comes from the notion of if we drew right here, mark on your plot, mark the average height on the y-axis. I know that because I'm just moving this point, I'm going across horizontally until I get right there, and that should be the average height. Just like down here, average weight, just like down here should be the average height. If I were to draw a vertical line, a horizontal line, straight across from the average weight, notice that I have my SD line here, and the regression line rotates down and is less steep than the SD line, so that the values that are above average are now closer to the mean, and the values that are below average are now closer to the mean. And that's what we mean by regression. We regress to the mean. Our regression line, we take our SD line and we apply the correlation coefficient, which pulls the above average values are now lower than the SD line, and the below average are higher. And so we have regressed to the mean. One other point I want to make sure that's clear is the SD line has this slope, but the plus times the sign of the correlation coefficient. So we can go in the other direction, in which case the slope would be the SD of y over the SD of x, and then there'd be a negative sign in front of it to denote it was negatively correlated. All right, I want to flip back to my picture that I actually went through the same process. I drew the SD line, which has a slope of the SD of weight over the SD of height, and it passes through that point of averages, the average height, the average weight. Then I took a strip of mothers that all have the same height to the nearest inch, and I looked through that strip and I located what looks to be the average weight for those mothers and see that it falls below that SD line. Then I looked at a set of mothers whose height is below average, and they all have roughly the same height. And for those mothers, I found the average weight, which is above the SD line. And then I fit a line through those points, and that's the regression line that passes through these graphs of averages. And the slope, again, is R times the SD of weight over the SD of height. It's hard to do that with the crab data because the correlation is so strong. It's like 0.9 3 or 4 or something. And so the SD line and the regression line are nearly on top of each other. But with the mothers, their heights and weights have a correlation of only about 0.4, and so you can actually really see this regression effect. So as you pointed out, the regression line is less steep than the SD line. And the notion of regressing to the mean is exactly what's going on here. Is on average, for this group of women who are above average in height, their weights are also above average, but not as much above as all the way as the same number of SDs. So how do we interpret this? If you look at one of your strips, you think about a mother who's the group of mothers who are 1 SD above average in height. So what does that mean? What's their height? What's the average height? What's the SD of height? We didn't actually compute that. So the SD in height is roughly 2.5 inches. The average, if we go back, let's go see if we can estimate that from here. So what's the average height? So you can now kind of look at the scatter diagram and come up with an estimate for the average height for the mothers in this study. What would you say? 64? Okay. And does 2.5 inches look like a good SD? I think so, right? What's the average weight? This is where the notion of the long tail is slightly problematic, right? The long right tail. What would you guess is the average weight? $120? $130? What? $125? Do you remember? You actually worked with these data at the beginning of it. Does anybody remember what it was? No? Okay. Maybe I'd go 130, 125, 130, and the SD is 10. Okay, let's go with 10. So when we go back to this question of how do we interpret the regression line, the slope of the regression line, if we think about, here's the average height for mothers at 64. Suppose we go up 1 SD. That's probably more than 1 SD, but let's go up 1 SD, which is up to 2.5, so it would be 66.5 inches. So of the women who are 1 SD above average in height, on average, their weight is not 1 SD above average, but it's R times 1 SD above average, which is 0.343 times the SD of weight of about 10 pounds. For the mothers who are 2 SDs below average in height, so they are 64 minus 5, so they're about 59 inches tall. Their weight is not, on average, 2 SDs below average. That would be on the SD line. But it's R times 2 SDs below average. Okay, so they are actually closer to the mean of weight. So that's how we interpret, that's how you can think of R times the SD of weight over the SD of height. It sort of tells you how to work out where the mean is on this regression line. So here's a picture going back to the actual data. Here's the SD line, which has a slope of about 8. And then because of the weak correlation between height and weight, the green line is the slope of the regression line, which is only about 3.6. So can you imagine what the residuals might be about this line? So that's the vertical deviation from a mother's actual weight to the point on the regression line straight above or below. Here's the residual plot. Yes, no real surprises here, right? We see that these weights have a long right tails, and you see that in the residual plot, is that this is not a nice blur all the way across the page that's roughly the same deviation away from the zero line. There are larger positive residuals. So when we use a regression line to make our estimates, there's a problem which is the same issue when we look at one-dimensional data and we take the center and the spread as the mean and the SD. We've got that same issue when we've got a long-tail distribution as we do here, which is that the SD isn't necessarily a good representative of the spread in this situation. However, there is no curvature or pattern in the residuals. Okay? Okay, I've got one last example for you. This is one of these hypothetical ones that tends to hit home because it's about quiz scores on tests. So suppose you have a score 27 points on a quiz. It's a total score. And we consider, it's the total number of points possible. We consider the score on the quiz and the points lost on the quiz for all the students in a class. What's the correlation between the score and the points lost? Or is there not enough information for you to be able to answer that question? It's what? It's obvious? It's 1 to 1. Is that obvious to everyone? So is the correlation 1? What does the correlation of 1 mean? All the points fall in a line. With slope, positive slope. Is that right? Yeah?
No, I think there's probably some mistakes with the GSI.
Does that enter the picture here? Even if the GSI made mistakes, there's still your score. Maybe you don't like your score because the GSI made a mistake and the number of points you lost. Yeah? What's that? Negative correlation. Negative 1? Or just negative? Can you two talk to each other and then come up with a reason why, like, let's take Warren's rationale and Pierce's, which says it should be negative. Why negative?
Because every time you lose a point, your score would go down. So if points goes up, score goes down, or score goes down, or score goes up, loss go down.
Right, so if you look at the pair of score versus lost points, as score goes up, lost points goes down. As score goes down, lost points go up. And so there's a negative association. That's why you're saying negative. And can you tell me why it falls on a line?
Well, why it falls on the line?
You can only have a correlation of 1 if the points fall on a line, or negative 1.
It's not like if you lose a point on the quiz, your score on the quiz changes by more or less than the point that you just lost.
So you can write an equation for that,
Okay.
which is the points lost equals 27 minus the score. So all values, all possible values, 27, perfect score, lost points 0. 26, nearly perfect score, lost points 1. 25, 2. Those points all fall in a line with a slope, a negative slope. Therefore, the correlation should be negative 1. So you didn't need to know even the total score on the exam. You could just have said lost points and score, and they are perfectly negatively correlated. So in that case, the correlation, because the correlation's -1, the SD line and the regression line exactly coincide. There are no errors about the regression line. You are perfectly estimating for any particular points or score I can tell you exactly what the lost points are. And just in case you wanted to prove it, here's the derivation of it, and I think it's a perfect time to stop. And I'm going to hold office hours right here in this room. We'll just pull up the screen, and I can answer any questions you might have on homeworks or projects.